Hi, everyone. Thank you so much for joining our session today. We're really excited about the content that we are going to present. We're going to give it just a couple more minutes. We see some more people joining, so we will start at about 2 minutes past the hour. Okay, we are going to go ahead and get started. Everyone, thank you so much for joining. We're very excited, like I said, about this presentation. It's extremely relevant for today as we hear more and more about the GPU. I would like to introduce our speakers very quickly, but I will go ahead and let them give a more thorough intro. So we've got on the Scream side, Yaniv Levin. He is an executive and a cloud expert, and he was instrumental in developing Scream Blue, our latest product offering. And we have Connor Jensen from Dataiku, one of our wonderful technology partners. And the two of you, oops, I'm sorry, I went ahead there for a second. I'm going to let you just go ahead and give some intros about yourself and discuss a little bit about the partnership and each of the companies, and then we will jump into the panel discussion. Yaniv, do you want to go first?
Sure. My name is Yaniv Levin. I've been in analytics for I'd say roughly 20 years. Started my path in finance, Wall Street, and then jumped over to tech. Most recently, I've sold my data analytics company, which I founded in 2015. Sold it to Scream about 3 years ago or 2.5 years ago, and now in Scream, in the product team, I'm in charge of the SaaS cloud products.
Awesome. And I'm Connor Jensen. I lead the field CDO team at Dataiku. Similar to Yaniv, I've been in and around the data and analytics space on and off for the better part of 20 years, over a few different domains. I started as a meteorologist in the US Air Force, worked there for a while, got a degree in mathematics, ended up in sort of catastrophe modeling in the insurance sector, spent about a decade in insurance as data science became sort of a corporate function. It helped build a couple of data science teams and platforms in insurance before moving over to tech about 7 or 8 years ago. And likewise, I've then sort of led data science and other customer-facing teams here at Dataiku, and now work to sort of help the CIOs, CTOs at our customers strategize where they're going with data and analytics and how the platforms can support them. So super excited for the conversation about sort of some of exactly that, of like, where is the technology going today?
Absolutely. So thrilled to have you both here. Thank you so much. We'll jump right into the questions. So Yaniv, first one for you. What are the key challenges that organizations are facing when they're scaling their data lakehouse infrastructure?
Right. So, we're talking about data lakehouse, but analytical infrastructure has gone through different evolutions. Were on premise 20 years ago, and then we moved over to cloud. There was a big hype around data lakes, which about 10 years ago, which kind of went down the whole kind of Hadoop landscape, and then data warehousing caught the central eye, and now we're kind of going back into data lakehouse infrastructure. And there are a lot of reasons for it, which I think some of them at least we'll discuss, but generally speaking, data lakehouse infrastructure is probably the most flexible data infrastructure you can build, and with today's tools, you can avoid the swamping that we had about 10 years ago. So specifically looking at data lakehouses, which I built from the bottom up at least 3 times over AWS and GCP. I think there are a couple of things we should look at from a number of different angles. So if you're kind of setting up your first data infrastructure and you're looking to set up a data lakehouse, I think the first thing is around setup complexity, right? So it's always going to take more time than you had initially thought. I think most companies talk about that. There was an article from Gartner's that said about 9 out of 10 or 85%, something like that, of companies that set up their first lakehouse end up basically underestimating the complexities and setting up different pipelines and governance frameworks and so on. Secondly, cost management. So cost management specifically around unpredictability. So, storage is cheap, but processing is very unpredictable. And 3, skill set, right? So everybody is either on cloud or moving to cloud. And when you build your data infrastructure, you need very specific capabilities, not only in building it, but also in managing it going forward. So at least most organizations, at least 50% of organizations claim today that they lack cloud set skills. So definitely if you're going into lakehouse infrastructure skills, especially around scaling them up, are much more robust, because when you build a lakehouse, data governance, observability, the file format, so on, are extremely important, and you need the right skill set to make sure. Now, if you're not gonna invest in governance and observability, just don't go there. Don't build a data lakehouse, because you're not going to be able to scale. Now, when we talk about scaling, so scaling the lakehouse is almost impossible if you don't have the right governance and you don't have the right observability tools. When you scale the lakehouse, I think the most challenging piece of scaling the lakehouse is performance and cost optimizations, because as we said initially, scaling computing resource, especially around EMR and Databricks and things like that, or just generally Spark jobs, there are always surprises and overspending. Some of that is due to their reserve instances versus on demand and things like that, or just by writing like bad code or bad queries. But some of that really has to do with the way we use compute processing resources inside the lakehouse, which most are unused. There was a very interesting article from IDC that talked about 60% cost. So 60% of the costs of managing a lakehouse are due to processes which are just not optimized. So I think those are the two kind of like core cases. There's also a case of migrating from warehouse infrastructure into lakehouse infrastructure, but that is basically a case where you have all of the above problems that we just mentioned. On top of that, it also encompasses basically managing two equally sustainable or two infrastructure landscapes which need to be sustained in parallel, at least for a certain amount of time. So those are my thoughts.
Yeah, and to add on to that, I think one of the things that I think is a huge challenge for moving into this lakehouse environment is sort of thinking through some of that history of where we've come to here. We very much sort of data modeling and data governance, and that sort of very much came to the fore in the last 20, 25, 30 years around the data warehouse idea, right? Like, how do we build these data warehouses, often for processes like financial closes or other sort of very, very regimented processes where it was a lot of work to get it done, but we were able to sort of say, this is very specific use case. This is where we're doing it. We're using it to tie off these reports that we have to file, this, et cetera. And that then became the foundation and the underpinnings for a lot of the business intelligence work, right? So we built these data warehouses, but again, a lot of upfront design, a lot of upfront work, and in a way that then from the business perspective, when you're like, oh, well, I need this report to look at something, or I'd like a dashboard to this, you're not able to do it yourself. You're having to go to the BI team or the IT to build it, and it's a very onerous process, again, because all of that design and all of that thinking has to happen upfront. And then once it's built, it's very immutable. There's not much you can do to sort of change or edit it or alter it. And so if you didn't solve the problem right the first time, it's a lot of work to go back and redo it. And so that was, I think, the push. And that was where I sort of very much moved from the world of analytics into sort of data science now about 10, 12 years ago, with that promise of Hadoop and the sort of data lake environment of schema on read instead of schema on write. And we can just put all the data into an environment where then people with the right skill sets can grab that data and do whatever they want without all that upfront processing. And what we ended up building was a whole lot of data swamps, right? Like, it was just data being piled into data lakes with no thought, no rhyme, no reason. You just sort of like went through the list of corporate systems and said, yeah, I want some of this, some of this, some of this, some of this, and then it was there. And you're like, okay, cool, but now I can't use it, right? I've got all these expensive data scientists, but they're not necessarily data engineers. The data's not really been put in a way that's helpful for them. And then when they try to tie it back to those data warehouse systems, it's almost impossible, right? Because of the amount of effort and work that goes into building those data warehouses systems. So then I can build some financial, models or things like that, but then being able to sort of tick and tie between what I'm filing from a GL, general ledger perspective or something like that becomes really impossible. And so the promise of Lakehouses is we find somewhere that sits in between those ideas of things that are really structured and that have very determined, very specific with all the governance and sort of figured out, but then the flexibility, especially for folks like data scientists or more advanced analysts who just need to be able to do things ad hoc and pull their own data to do it, that you have the flexibility of the sort of data lake to be able to grab what you need when you need it without having to have spent all the time designing up front. And that now we sort of have an environment that in theory serves two masters, right? It can serve that sort of like very regimented data warehouse type stuff, but also needs to be able to serve for data lakes. And they're not 100% opposing, but they are definitely competing priorities. They're different frameworks and how people need to think about them. And so the way I've seen sort of this fail a lot of times, and the real challenge here is you said, you have to be thinking about how are you going to do the governance, how are you going to set up the observability, how are you going to do it up front. And so you either have people who come from the sort of like really regimented old school, for lack of a better word, but I don't want to say pejoratively, right? But just sort of like that, like more rigid mindset and very prevalent in sort of people who built finance data warehouses and things like that had to be precise. Like, there's no room for error. That's a really heavy-handed form of data governance that ends up being put. And then you have people from the data science community, and then this, I'll be pejorative about myself here, who are just like, yeah, whatever, give me all the data and we'll figure it out afterwards, right? And it's like you have that, neither of those approaches work sort of in this right world. You have to start with where you are, use the data that you have, and use it for the right use cases at the time. And so you're both have some thought up front about that governance and, not overly heavy-handed, allow people to move forward and work, but then it's living, it's breathing, it's changing, and you're updating it. And like finding that right balance between those is extremely hard, even at a small scale, right? And then you start thinking about this from an enterprise perspective, where I'm talking about systems from M&A and all these different things, then that just like, it becomes sort of like an exponentially larger problem.
Wow, first question, and this is already a fantastic discussion. Thank you both. Really quickly, one thing I forgot to mention before is that we will save some time for Q&A at the end should there be questions. So if you do have a question throughout the session, feel free to use that questions box at the bottom of your GoToWebinar panel. So again, thank you. Next question, Connor, is for you. What are the impacts of legacy technology decisions on companies' ability to move forward?
Yeah, and I like to even sort of, it goes right off of some of what I was just saying is, with we have nobody gets a clean sheet of paper, right? This is the way I often it's like, as data architects, it's nice to sit down and sort of start from a clean sheet of paper and say, what does our ideal state data architecture look like? Where's our source systems? How do we ingest it? What are the pieces? And, we can draw pretty boxes on paper, but then we turn around and we look at the real world, which is systems that have grown haphazardly over a long period of time, some of which, especially you see this a lot in financial services, you see this certainly in the pharma space, but anywhere that like they've been doing data analytics for a long time, often have like very rigid old setups, sometimes still mainframes in place, things like that, which don't really then sort of talk to our sort of newfangled data lakehouse technology that we want to do. And I remember when we built our Hadoop on-premise system about 10 years ago, having scripts that started in COBOL and ended in like Pig to drop it into the data lakehouse, right? And so, or the data lake, and like that amount of hoops you have to go through just to get to the data is a huge starting point. And we are so much legacy technology in companies. And then, you think about, especially in the enterprise space where we focus, nobody has just been one company for a, monolithic, or I shouldn't say nobody, but very, very few companies have sort of been monoliths for a long time. There's M&A, there's new product launches, there's all these different things. And so you have systems that you have, trying to think of my favorite one recently. I was talking to a customer who was like, oh yeah, well, we are just now at the end of a 5-year journey to reduce our 19 ERP systems into one, right? And that's like, I remember that one just because it was because it was a prime number because I'm a nerd, but I was just like, that's a lot of ERP systems to go through, right? But that's not unusual, right? You see that all over the place where, you've got these like super complicated, even if it's not old legacy technology that makes it hard to work with, you often have replicated systems doing the same thing in multiple different ways. And that's not just a technology problem. Now you have to go to the business users of that and say, okay, we have 19 systems that all define, premium this way, or they define cost that way, or they define something. And those changes or those differences can be really subtle, but when you have 19 different business units with 19 different systems defining the same thing 19 different ways, you've maybe solved it on the back end for a reporting purpose to file your ledger, things like that. And I realize I'm getting a lot of finance examples, so there's obviously this sort of thing applies in supply chain stuff, it applies in inventory, it applies, there's a lot of different ones, but we have to be able to live with the technology that we have. We can't ignore a business unit because we don't like to work with that technology or it's harder. We need to have a plan to get there. And that's just like a small sample of it, but I think it really does come down to just that we've got old technology that can be hard to work with. We have duplicate technology that's all solving the same problems, that we need to come up with the business rules before we can do some of the technology work. And there's a lot of education that then has to happen into the business to be able to have those conversations, right? And so that, I think, really does slow companies down. And the bigger you are, I think there's still sometimes this idea that we should build one lakehouse, right? And that, we should have a company-wide lakehouse. We think about that, and we always, I think we default to that from the sort of the data side of the house because that seems cleaner and easier to us. But I even challenge that that's the right approach, right? Sometimes you should have different things for different purposes, but again, with intent, not just because you're like, this is too hard to solve, you guys build your own and we're going to build our own. Like, say why you're going to do those things and have different things for different purposes. So yeah, that existing technology landscape, like none of us get to start from scratch. We've all got data, we've all got systems. There's a lot that we have to figure out the path forward without sort of leaving the past behind, and that is really hard to do and takes time. And very rarely do we give, as Yaniv talked about at the very beginning, the effort is often underestimated. And this is an example of why that's underestimated. Is these aren't projects that are 6-month projects or 12-month projects. Right? Really doing this is a project of in full years to get there, and corporate decision making and life cycle. And to be fair, the average tenure of a CDO isn't even long enough to see one of these projects end to end. And that's part of the problem, is everybody's like, oh, this should be done in like a year. A year's elapsed and everybody's like, oh, we haven't solved this problem yet. And then we're going to get somebody else who will not solve it in the next year. But yeah.
Yeah, basically whatever you planned, double the time.
Totally. So yeah, I don't know, that's my take. I don't know I'm curious, especially Yaniv, as you're thinking about as we evolve into the newer architectures, how is that sort of like old, or how is that sort of legacy technology decisions impacting it on the compute side?
It's a good question. You know, it's two different, or we've dealt with it with two different layers. So one on Panoply, when we managed Panoply, when I managed Panoply, so Panoply dealt with very, very, it was kind of like an analytical architecture in a box, right? So you connect your data sources, and then you have your kind of like tiny warehousing, and then you have your automated ETL, you have your tiny warehousing, and then it connects over to whatever BI tool you want, either internal or external. And with that kind of architecture, we completely ignored the historical architecture, and what you had to do was basically maneuver data from your legacy architecture to the new one. That worked only for small and very tiny, medium-sized companies. And usually in larger organizations, what happened is that they used that architecture as a data mart. So they had their legacy architecture as and they didn't touch it. But they had legacy architecture, which IT was in charge of, and IT managed, and we didn't touch it. And that and some sort of edge business unit would take Panoply, connect their sources from the legacy architecture, and then use Panoply as their kind of like independent automated warehousing on the edge. So that's how we dealt with Panoply. With Scream, so Scream has three products, right? Their core product is a GPU-based database. On-prem also have cloud implementation, but historically it was built for on-prem use cases. With Scream, the path to deal with legacy was we basically met the legacy infrastructure, and we met the core central repository. And then what we did there was companies that went through a process of I'm missing the word here, but making their legacy infrastructure newer, kind of going through an evolution. What they did is that they would take Scream and replace, and in different steps, kind of replace different processes inside the architecture. So they wouldn't have to replace everything, but some stuff that became too complex or some processes that became way inefficient, they would basically replace small pieces of it with Scream's processing. So it was basically a process, like multi-year process of each year or each quarter replacing a single piece until everything was kind of like renewed.
Yeah, and it's interesting. I think that actually speaks to when you talk to CEOs or you talk to companies, there's often the sort of, oh, well, we're in now it's cloud migration, or the last few years it's been a lot of cloud migration, or we're moving everything into this cloud data warehouse, or moving into this like cloud data lakehouse system or whatever. But there's, I think, this like corporate perception that we get to finish the data work, right? And like I think I think part of it, because I don't know, I'm philosophizing a bit here, but I think it's because data has so often sat in IT as an IT type function, and IT exists around the idea of sort of like system management and project management, right? And so there's, they scope well, we're going to build a data warehouse, and you go, okay, cool, and then they build the data warehouse, and then they go, check, we're done. But like that's not how data works, right? The data, there's still new data coming in every day, every hour, every minute, every second, whatever that particular data is. And you only stop getting new data, or you stop having the data change when you go out of business, right? So as long as you're still functioning, you're getting new data, and that's evolving. And I don't always feel that, like, the way we think about, from an IT perspective, working with data, we think about it a little too like the sort of like, oh, I built this app, or I built this application, or I built this service bus, or I did whatever. And like, if I built the service bus, it works until I break something else, right? Like, or I build this piece of code that sits in an application. That application is going to run until somehow or other I screw something else up that like propagates through the system and breaks it. But data isn't that way, right? Like, data formats change, data styles will change, upstream, downstream, use cases, all that. Like, it's constantly living. And I just, I feel like we sort of sometimes apply the wrong approach to managing these going forward. And some of that maybe just come from the sort of like legacy mindset approach to how we dealt with, because it used to be, oh, well, I installed, here's my IBM IIM infrastructure, and I dropped it in, and it's vertically integrated. The compute and the storage and the application and everything happens in one, and that's just not how our systems live today.
Okay, thank you both. We were going to try to keep this to 30 or 40 minutes, but I'm guessing now we might take the whole hour because these are really great discussions. Yaniv, next question is for you, and this is sort of a multi-part question. So um, first part, what are the most compelling use cases for GPU in data processing, and how do they compare to traditional CPU-based approaches? In what way can the integration of GPU in data lakehouses enhance the performance? Can it enhance performance? And can you provide specific use cases or performance benchmarks that highlight these improvements?
Okay. Right.
No pressure,
So
though.
long question. Yeah. So streams, like stream technologies, IP is around efficient utilization of GPU instances for analytical processing. And that's why we're kind of super focused on GPU involvement, and whatever we can do around to open new use cases around GPU. Now, so GPUs weren't initially built for analytical purposes, right? They've kind of like adopted. And now there's this whole hype around GPUs because of AI, and that hype is going to go down at a certain point. And there was a huge hype around GPUs a couple of years ago, where the whole cryptocurrency thing came out. But again, that's not its initial purpose. So GPU, we won't go into exactly how GPUs are built and everything, but very generally speaking, they have a ton of cores. And those cores are about 25%, have about 25% the power of a CPU core, right? So they have a lot of cores, but they're very weak cores. So, and the reason for that is that GPUs are basically built for massive parallelization. So wherever there's massive parallelization needs in analytical use cases, that is obviously where you probably get some price performance. At least in the historical cases, you get some price performance using GPUs instead of CPUs. So they have very strong raw processing power, and they're good for repetitive, computationally intensive operations. So, generally speaking, things like matrix operations, training machine learning models, and so on, that's where GPUs would traditionally be very, very strong. But CPUs are optimized for kind of single thread performances. So where CPUs would traditionally be very strong is where you have these sequential processes, sequential computing processes. The sequential computing processes are most of the processes in for analytical purposes, and therefore, for most use cases, at least traditionally, using CPUs for analytical purposes would probably be better. in the cloud, there are also different thoughts around that, different applications. Also, because CPU, you could much more easily get CPUs than GPUs. Now that's not the case. Now is an abundance of GPUs around. Now, what has happened in the last couple of years is that I think NVIDIA, who's in charge or who dominates the GPU market, kind of understood that GPU use cases are kind of like popping up every couple of years, but it's kind of like by chance. And at a certain point, they're going to be taken over, and their market dominance is going to go down. So they've started kind of giving more applications towards the or more love towards the application layer, which I think is super smart and super needed. So now with Rapids, you can use GPUs for sequential tasks that in the past weren't possible. So you could actually use GPUs for ETL processes because, well, ETL processes are not always sequential, at least not all of them. But now with Rapids, with the application layer, it does make much more sense. And I think to use GPUs for analytical purposes. And that's just going to evolve. There's no way it's not, because GPU prices are going to go down because of the abundance. There is NVIDIA's monopoly is going to go down because, especially around AI, Amazon and Microsoft and Meta are all building their own chips. So the GPU use case for AI is going to go down. So they're going to need to find more use cases for GPUs, and that's going to be the application layer. Now, specifically here, in Stream, we've been using NVIDIA's GPUs for a very long time. Our whole IP is around NVIDIA's GPUs. Our whole IP is around analytical purposes or linear analytical purposes. We have proprietary algorithms. We have IP around query execution and so on. That basically what that means, or what that transforms to, is that even compared to Rapids, we're able to kind of like squeeze all the juice out of those GPUs to get a very, very extreme cost performance basis. In the past, we talked about the on-premise use cases, and Carter mentioned the legacy use cases and the legacy infrastructure, and we talked about how with StreamDB we used to go like one by one, like thread by thread by thread, and there in the legacy use cases we always used to go up against Hadoop use cases on premise, and they're using GPUs with our IP compared to using CPUs. Our cost performance was around 1 to 10, right? So we were able to, on the same level of performance, lower price by 90%. On cloud, that's not really the case because cloud architecture is a bit different, but on cloud, we're also able to lower cost performance. Really recently, we had benchmarks compared to Databricks, for instance, that we were ×6 performance at same cost. Just really being able to squeeze all the GPU, all the power out of GPUs, because when you look at GPU processing power, it's multi-times stronger than a typical CPU. Like when you look at the average GPU and the average CPU, the thing is that it's just not built for linear processing. But if you're able to kind of somehow squeeze all that processing power for your linear processing, you're able to get multiple times faster, like much better than times 10%. Because just looking at the average, you're looking at like 700 cores compared to 4 cores, right? Or 700 cores compared to 6 cores, right? Now, even if those cores are like 25% of the power, you're still going to get like much stronger processing power when you look at CPUs. So basically, I think when we look at GPUs right now, and I'm saying GPUs because that's what we have right now, but I'm sure that as the use cases progress, right, these new chips are going to come out. They're already coming out, right? Amazon already came out with a new AI chip, and Meta already announced at least the name of their new AI chip. Those chips are specifically their processing power is specifically geared for AI LLM training, right? So when these new chips are going to come out, the processing power is going to change and vary, and that's going to have a whole new wave of new applications. analytical applications inside the Lakehouse infrastructure that you're going to build.
The only thing I'd add to that, because I definitely am not going to go nearly as deep into that, because that's not my wheelhouse. Obviously, that's a niche. But the thing that I like from a speed perspective is just the ease and speed of use of this stuff, right? So talking about the move from CUDA to Rapids, talking about using things like Scream, or more to the point, talking about going from writing things in Hadoop and having to write HBase or Hive or Pig, or like as Spark came to the fore, moving things into PySpark and all that, or learning Scala and stuff, right? Like Spark tuning was brutal, right? So the promise of Hadoop was the parallelization that we're describing from the GPU perspective. That was what we were trying to get, was parallelization across cheap CPUs, right? Like that was what Hadoop was supposed to give us. And my background's in math, not computer science, but I've worked in this space long enough that I've had to learn to code on and off in a lot of languages over the years. And like I remember, maybe call it like 2015, 16-ish, like learning Scala and PySpark to use Spark, and I was like, I'm out, I'm done learning. This is like so brutal to do, and there was so much that you had to learn as a data scientist to be able to use that effectively. That obviously was then this last decade. Since then, things like Databricks made it so you didn't have to start thinking about it. And Kubernetes continues to sort of, it's like we're continuing to make it easier and easier to leverage that technology, so that as the technology itself gets faster, it's also, I don't have to go and think through and tune Spark anymore. I don't have to do those things. And like this now moving into leveraging GPUs for these, and even getting away then from sort of like how the Hadoop technology did that across CPUs and moving into GPUs, that itself gets faster under the hood, but also gets faster on top of the hood, because we're able to just be able to I don't have to think about that when I'm coding anymore. I don't have to think about that when I'm building my projects and thinking how to do it. Like the architecture is much better at optimizing itself to use it. And that's what I think is so cool. And again, makes my life so much better, because it's just not where I want to spend my time, right? I'd rather spend my time like getting the data ready, analyzing the results and things like that, not hard tuning of the infrastructure.
Great, thank you both for those answers on a quite complex question. Connor, next one is for you. When you're looking at the scale of data many companies are using now, is increased compute power really a challenge?
Yeah, that's an interesting one, because I sometimes feel like when we're really focusing, especially on, and I felt this a lot in the ML ops space in the last few years too, and even still now, from sort of as people are talking about like speed of inference, now that we've moved into the sort of the Gen AI stuff, is that that often feels like we're solving 1% of the problem, right? When I look at the actual data companies are often using to solve what they're doing, it's little data, right? Like that's like, it's not, and obviously big data has fallen out of the vernacular, because one, it was too amorphous to define, and what that meant for one company versus another was very different. But also, I sometimes felt like there was sort of what we were solving on the technology side of the house sort of felt like solving Silicon Valley problems, and you're solving the data scale problems that Google has, that Meta has, that Amazon has, and then you're sitting, and I mean, obviously other sectors have some use cases like that, right? When you're sitting in a bank, you're dealing with stream data and the sort of stock market stuff. Like that's big, high volume, fast moving data. If you're Walmart and you're processing your logistics stuff, that's big. It's a lot of data. There's all that sort of stuff. But it's still the 1%. You're talking about the top end of the biggest companies in the world dealing with that, or you maybe have 1% of use cases that you're trying to solve that have data like that. And the other 99% of companies and the other 99% of use cases aren't big data problems. And so I wrestle sometimes with where I feel like on the technology side, we're solving to how do you do the, this ML ops stuff of how are we going to have HA parallelization of API nodes to do this, to manage, 10 million queries a second or stuff like that. And I'm we're talking 10 queries a day, right? In the real world sometimes. But what I do think is really interesting some of this comes when you talk to people like in the business, and you're scoping a problem, you're scoping what you want to work on, and you say like, well, how fast do you need responses? The answer 9 times out of 10 is like real time, and I'm like, okay, cool. What does real time mean to you, right? And it's really often that they're like, once a day, and I'm like, oh, okay, right, like, cool. I think we can manage that. I don't think it has to be real time, because real time is hard. Like actual real time is really hard to do, but micro batch, micro processing, all these, there's things that we can do where, like we're talking about, sub-second responses to queries and things like that, where the person is like, oh no, like I'm just used to having to like click a button on Friday and I go home for the weekend and hope that it works by the time I get back to work on Monday. So having this sort of increased compute power is a problem for a lot of people, not necessarily to this like sort of like the dramatic scale that we sometimes talk about it, but where I think this really comes into play is in giving that ability to use this compute to average people, right? And I think that that's where we continue to sort of have this gap, is that on the one hand, we've got these systems that can do just like massive data, super fast, all these sorts of things. On the other side of the fence, we've got somebody sitting in Excel or in a 25-year-old .NET application that their company created or something like that, where like clicking something that we all know, if I was doing this in an optimized way, is, maybe it's not sub-second, but it's something that's like, going to take my system across some GPUs a couple of seconds to do at worst, right? And in the current whatever spaghetti chain of sort of like architecture we got is a 15-minute response, a 30-minute response. It fails half the time because it times out sort of response, right? And so taking what we are creating in this and making it more accessible, making it so that like that Excel user who's used to having, oh no, this giant spreadsheet that I have that has 500,000 rows on it and takes overnight to process when I need to do an update, is like, yeah, hey, that's all happening locally, of course, and Excel is not optimized to do any of these things. And even in the world of SQL is something that would only take minutes. And in the world of, now distributed analytical processing on GPUs is seconds, right? Like, but that barrier has still been, oh, you want to do that? Cool. Like, go learn how to write SQL, go learn how to write Python, go learn how to, work with this. And so we need to continue to make these things where all these advances we've made under the hood become more accessible to the other 99%.
I absolutely agree with that. I want to touch on 2 points that Connor just said. One, in Panoply we had the exact same challenge, right? In Panoply we dealt a lot with ETL processes. We automated ETL processes. Well, we still do. I'm just not in charge of it anymore, right? But we automate these massive ETL processes, and we had the exact same question, right? What's the speed of ETL that you need? They're like, oh, we need real time, and then you're like, okay, fine. So if we charge this for daily, we charge this for hourly, and we charge this for 10-minute ETL processes. All right, so all of a sudden, daily is fine, right? The terminology is very important. Secondly, in terms of like the abundance of compute, like on cloud, you don't have a problem with compute. There's, as far as you're concerned, there's infinite compute resources. What you do have a problem with is the cost. And what Connor had mentioned, I saw this multiple times, right? Because when you're on premise, you can write bad code, but you're still going to pay the same because you have your servers on the racks. On cloud, you have infinite resources, like infinite, but then you come with the same mentality onto the cloud, and then all of a sudden at the end of the month you get these bill spikes. So the understanding of how to write the SQL, how to write the Python, the understanding of how to use these compute resources efficiently is way more important. It's like the most important thing in terms of what kind of knowledge we now have to incorporate. And I think the main barrier in terms of like smart utilization.
Yeah, Look, I'll say this is my favorite hot take. Data scientists, by and large, are shit coders, right? Like they think that they're really good at it, but the vast majority of data scientists, they're not computer scientists, they're not engineers, they don't know how to write good, efficient production code. And it's been the struggle of a long time, is sort of like giving them access to more resources, giving them, the freedom to work with these things. And sometimes like when you're training, if you're training like a big ML model and stuff, like at best that's going to take a big chunk of time and be a lot. But like, we see this a lot where we're sort of dealing with, because in our platform, people can both, we have components that will write the code for you, right, and do sort of more visual stuff, but then you can also spin up a notebook, you can spin up a code studio, you can write your own code. And very frequently when we get a call or a complaint from a customer that like the system is crashing or it's running really slow or things like that, like I don't know that I'm going to say 9 times out of 10, but 99 times out of 100 probably more likely, like you go in there like, oh well, here's these like 2 notebooks that somebody wrote that are really inefficient code, they've got it to run and it is just hogging all of the resources of your underlying infrastructure. Or if you've given people unlimited, it's the like, holy shit, what did somebody do that just cost us $10,000 over the weekend, right? Like, and so like we like that is a huge problem, because it is still, sometimes there's still hardware constraints. If you set things up smart to not have those sort of like giant spikes in cost, or I guess just didn't say smart, if you set things up to be more restrictive, to make sure that you protect yourself from the cost, that's smart. But then suddenly you've got one person who's hogging all the resources. The other side of the coin is you can absolutely run up these massive bills from bad code, right? And so like, how do we give people more flexibility and more power and availability to this stuff without running up these like massive bills, which is dangerous.
All right, so I do have 2 more questions for each of you, but I'm just going to do one each in the interest of time. And then I think if we do have questions come in, I'm going to turn all of these questions into a blog. So if someone has a question that we don't get to, or that you think of after the fact, please send them. We'll have contact information at the end, and all of that will be answered in the blog and it'll be published. So no worries there. The questions will get answered. So Yaniv, last one for you. What do you see as the ideal data infrastructure in the coming years?
Okay, I can talk about this for a full hour, but I'll make it very short. So just like very like bullet points, right? So 2 axioms, at least for now, cloud and Lakehouse, right? With the technology we have right now, it's going to be on cloud. It's not going to be on premise. It's going to be on Lakehouse. If you have legacy architecture infrastructure, which most enterprise companies have, then it's going to be hybrid, because you're never going to be able to move, not in the next century, you're not going to be able to move your entire infrastructure over to cloud. So it's going to be a hybrid approach. So those are the axioms. When you have a unified approach, and when you talk about cloud and when you talk about Lakehouse, data management, data observability must. You can't scale a data lakehouse without understanding which wire connects which wire, i.e. processing, connects this table to that table. You can't manage a lakehouse if you don't know how much that wire costs. Aside from that, serverless, serverless approach, but that of course comes with the cloud. And then the last point, which I'm not going to talk too much about, but in the coming years, because Amazon and Microsoft and Meta, and of course some legacy companies like NVIDIA and Intel and AMD, are all in the process of developing new types of chips for these new types of use cases on cloud, not necessarily analytical, but new types of use cases. For instance, the new chips for AI. I think that inside the Lakehouse, we're going to see a much broader supply of processing hardware capabilities. So just like as you build out your Lakehouse, whether it's a full cloud Lakehouse or a hybrid approach, take a look and make sure that you're aware of all the hardware capabilities that are coming out to the cloud, because some of these, just like GPU, right? Some of these will have direct implications on your cost performance in the your cost performance capabilities in the Lakehouse, which will then enable you to have much larger, much larger capabilities in terms of your use cases. Very, very quickly, I talked about that, and those are my bullet points, but I could talk about this for a full hour.
Totally with you on those.
Okay. Thanks, Yaniv. Now, Connor, last one for you. While data infrastructures have had a lot of innovation over the last couple of decades, it hasn't really changed how most people work with data, as in spreadsheets, that sort of thing. How do we finally change that?
Yeah, and that's where I think the future state architecture that Yaniv was just talking about, one of the things, we think about the infrastructure side, like that sits at the bottom. Where does my data actually sit from a storage perspective? Where does it get, where does the compute happen? Like, we need to continue to build the layers on top of that to make it so that it's no longer that sort of like vertically integrated approach to things, because that's where most people still are sort of used to like, well, where I interact with the data is where something's happening to the data, right? I'm in this application, it's sitting in the database that's attached to that application, or I'm in this SQL warehouse and this is where it's all happening. And sort of like the idea of the tiered architecture that we've been working towards as an industry for a long time is, it's like I think right now there's maybe sort of like 3 different layers there that we need to focus on. One is that somewhere there's actual metal upon which these things are happening. Then above that is your data layer, and that's where you're building the structures, the semantic layer, the Lakehouse, the pieces like that. And then there's a UI layer on top of those that I think can also be distinct from that. And like, we need to continue to abstract somewhat for most users away from the data warehouse, the Lakehouse, the data lake, et cetera, and away from that actual like base infrastructure and where the actual servers where the stuff's happening, or the cloud, or the whatever, because this will continue to evolve and change, and this will continue to evolve and change. And right now, every time you move from one cloud to another, or you move from one infrastructure within that cloud to another, you end up having to rebuild whole parts of the data piece. Or you had built this cloud data warehouse and then it wasn't performant, it wasn't whatever, you switch to another one. Everybody has to sort of rebuild everything every time, over and over and over again. And we need to continue to abstract away so that you have a place where people can interact with it. And again, as many people as possible, right? There's no one perfect UI that every person at your company is gonna be able to work with, but make those as few as possible that then insulate those users from these under the hood changes that are happening in the actual sort of like data environments and the actual sort of like infrastructure environments. So I think that's where that has to go, because we just can't have to, every time we move something below, we have to rebuild everything on top. That just doesn't work. We've seen it not work for a long time.
Anything to add to that, Yaniv?
I agree 100%. I have like absolutely nothing to add.
All right. Okay, give me just a second here. Can you confirm if you can see that ending slide?
That's up there.
Is it in presentation mode? I'm sorry.
It is not in presentation mode. It was at first.
Well, it should be, but I apologize for that. If anyone does want to, hold on, you know what? I apologize to the audience watching. There we go. So if anyone wants to contact us, feel free to scan this. And then, as I said, we will be publishing the questions answered today in blog form. We'll be publishing the recording on our website. And so there are many ways to contact us. If you have an additional question, if you want to reach out to either Dataiku or Scream, we'll be happy to talk to you, show you a demo. So Yaniv and Connor, it's been a pleasure, and I think the conversation was excellent. Thank you so much for joining us today.
Yeah. Thanks for having me. It was a lot of fun today.
All right, to everyone watching, we really appreciate you registering and joining, and have a great rest of your day.
Bye, everybody.